In the previous lecture, we looked at how to set up the reliability problem, and one of the things we discussed was how to identify whether a problem is a system reliability problem or an element reliability problem. So these are the questions that we asked. Is the system of interest made up of two or more units that are logically or physically connected? And the key point here was that the item's performance, whether it's working or not working, can only be given in terms of those of the constituent units. So if the answer was no, then we have an element reliability problem. And if the answer was yes, then we have a system reliability problem. So that's what we are going to look at today in a more formal manner. We have looked at how to describe systems in terms of very simple combinations, unions and intersections in the previous lectures, but today we are going to look at various ways in which we can represent a system in terms of its constituent elements. So the system is constituted of its elements, and its performance can be given in terms of those of its elements. So that's our starting point. Let Fi be the failure of element I, and we have looked at these two cases already. The simplest representation of a system made up of binary elements are the series system and the parallel system. That word binary is important, and which basically means that it can either be in up state or down state, safe state or failed state, working state or not working state. And that is the most common representation that we take in systems reliability, both for elements and for the system, and what we will do for our structural systems as well. So for a series system, every element must work for the system to work. So that is the logical representation of the series system. So the failure of the system for the series system is the union of all the individual failure events, all the element failure events. So it's F1 union F2 all the way up to Fn. Looking at the system survival, or F-sys complement, that is the intersection of all the individual complementary events. So all elements must work in order for the system to work. The system reliability for the series system then is the probability of the intersection of all the element survival events. So P of F-sys complement, or the reliability of the system, is P of F1 complement intersection F2 complement all the way up to Fn complement. If the elements were all independent, or mutually independent, then the reliability of the system is simply the product of the individual reliabilities. This is also one of the drawbacks of the series system, because even if an element or all the elements have high reliability by themselves, but the product of each of those finally might lead to a number that is not high enough. So that is one of the essential drawbacks of the series configuration. On the other extreme, for a parallel system, the system works as long as at least one element works. So that's a very benign configuration, and we can express the system failure as the intersection of all the failure events, all the element failure events, or conversely, the complement, the system survival, is the union of the element survival events. So the reliability of the parallel system is 1 minus the system failure probability, which is simply the product of the which is simply the probability of the intersection of all the events. So system reliability is 1 minus P F1 intersection F2 all the way up to Fn. And if the elements were mutually independent, then the failure probabilities are the product, the system failure probability is the product of the element failure probabilities, and the reliability of the system is 1 minus of the product of all the system failure probabilities. So that would be the simplification for parallel systems if all the elements were mutually independent. Now, unfortunately, real systems are rarely this simple. So it's often highly idealized. It's too idealized to represent a system as a series or a parallel configuration, and that too with independent components. Take, for example, this particular case. It's a parallel system, but the elements are dependent. So we can express the system failure probability as the product of the chain, where on the right you see P of F1 and then P of F2 given F1 and then so on F3 given F1, F2 and so on, all the way up to P of Fn given F1 intersection F2 all the way up to Fn minus 1. Now, if they were mutually independent, then this would simply be the product of all the individual failure probabilities, which if they're not mutually independent, the problem is then these probabilities, especially when we have several conditional events, F1, F2, all the way up to Fn minus 1, those terms quickly might approach 1 because of load sharing, because of dependence, and so on. So in such an example, the benefits of the parallel configuration would not be realized to the extent that we would if they were all mutually independent. So these are some of the things that we see in real systems. So for real systems, more complex system logic may be necessary in most cases. Because, as we said, element failures may be dependent events. Not all elements may be loaded at the beginning. So these are the different situations which would require more complicated modeling. An element may have more than one failure modes. I mentioned binary elements, but if an element is not binary, if there are multi-state failures, I have given 3 examples. A diode that can fail either in an open or a short configuration. So it's a 3-state system. A pump that works fine, then works at half power, and then doesn't work at all. So it's again a 3-state system. A truss member which is either working fine, but then in compression it buckles, and then in tension it has a completely different behavior. So these are multi-state systems. In such cases, we might need to look at different ways of modeling the system. There are different methods, and let me list some of them and then indicate which ones we are going to look at in greater detail in this lecture. So one way is to look at simply the state space of the system, and that's possible if the state space is finite in size. And this works whether the system or whether the elements are binary or multi-state in nature. So this method can work in both situations. Then we have the method of the structure function, and especially if we can assume or if we can conclude that a system has a monotone structure function, then it becomes somewhat easier to model it. Then we have the reliability block diagram, which is also a very useful, very popular method in modeling systems in terms of its elements. The fault tree, another very popular method. The event tree, Bayesian belief network, cut sets, especially, and then within the cut sets, we really like to look at minimal cut sets, and we'll discuss that, and its complement, the path sets. So the items that are marked in red, the RBD, the reliability block diagram, the fault tree, and cut sets, we're going to look at more detail during this lecture.